Hello and welcome to Dr. Jim's Structures class, where we do structures by example. Thanks for tuning in.
Man's practicing fuzzy math again.
This video is part of a series of videos on drawing axial force, shear force and bending moment diagrams for simply supported beams. Today's example introduces applied moments by analysing the simply supported beam shown on the screen. So let's get to it. The beam spans 6 meters, has a knife edge support at A and a roller support at C. It carries an applied moment of 120 kilonewton meters at B and a downward point load of 30 kilonewtons at D. As usual, we will start by finding the reactions. Draw a free body diagram bubble that cuts the beam away from its supports. The purple lines represent cuts that will expose the unknown reactive forces. If this makes little sense to you, click the link on the screen to find out more about cuts, free body diagrams, bubbles, and all sorts of cool stuff. Now draw the free body diagram for everything in the bubble. Remember to include the support forces that have been exposed by the cuts. The reactions are found by applying the equations of equilibrium to the free body. We're dealing with a plane structure, and that means there are a minimum of 3 equilibrium equations available to us. These equations are commonly expressed as horizontal forces must sum to 0, vertical forces must sum to 0, and moments about any point must also sum to 0. Starting with horizontal equilibrium, we see that HA is the only horizontal force, and because horizontal forces must sum to 0, HA must be 0. Inspection of the free body diagram shows that taking moments about A will yield VC. When writing equilibrium equations, always say what you're doing. Start by stating the sum of moments about A equals 0, and that counterclockwise turning effects will be taken as positive. The resulting equation shows that VC is plus 60 kilonewtons. Next, summing vertical forces shows that VA is minus 30 kilonewtons. Replace the labels on the reactions with numerical values. Next, erase the calculations and the free body diagram bubble to tidy up the screen. This wouldn't be done if working on paper. If you want to see a more detailed video on finding reactions, then click on the link on the screen. To proceed, we need a sign convention for axial force, shear force and bending moments. Here is a graphical representation of the sign convention we will use. The boxes represent a thin element cut from the beam. Note, tensile axial forces are regarded as positive. Shear forces that try to spin the element counterclockwise are regarded as positive. And bending moments that put the top face of the beam into tension are regarded as positive. In other words, hogging moments are positive. In previous videos, we used the universal truths about axial force, shear force and bending moment diagrams to make the analysis simpler and more efficient. However, as this is the first analysis to include an applied moment, we must go back to first principles to figure out what's going on inside the beam. In other words, we must set up algebraic expressions for the internal forces in the beam. To figure out what's going on between A and B, draw a free body diagram bubble that cuts the beam x meters from A. Next, draw a free body diagram for everything inside the bubble, including the unknown internal forces inside the beam that have been exposed by the cut. Note, you should always assume the forces exposed by the cuts are positive. The arithmetic will sort out the actual directions. Note also that this free body diagram is good for only the first 3 meters of the beam, because if x is greater than 3 meters, a different free body diagram is required, a diagram that includes the applied moment at B. Summing vertical forces shows that the shear at X is plus 30 kilonewtons. Taking moments about the cut shows the unknown bending moment is plus 30x kilonewton meters. This tells us that the bending moment varies linearly from 0 kilonewton meters at A to plus 90 kilonewton meters at B. Now draw and label baselines for the shear force and bending moment diagrams. Note there is no diagram for axial force as it is known to be 0. Plot the shear force and bending moments for the first 3 meters of the beam. Next, we need to find out what's happening between B and C. But first, erase the calculations and the free body diagram bubble. Now draw a free body diagram bubble that cuts the beam between B and C. Then draw a free body diagram for everything inside the bubble, noting that this free body diagram is good for all values of X from 3 to 6 meters. Summing vertical forces shows that the shear is plus 30 kilonewtons. Draw this result on the shear force diagram. Taking moments about the cut shows the unknown bending moment is 30x minus 120 kilonewton meters. This tells us that the bending moment varies linearly from minus 30 kilonewton meters just to the right of B to plus 60 kilonewton meters at C. Draw this result on the bending moment diagram. All that is left is to find out what's happening between C and D. Tidy up the screen, then draw a free body diagram bubble that cuts the beam between C and D. Note that the bubble encloses the substructure to the right of the cut. This has been done to simplify the free body diagram and calculations. Draw a free body diagram for everything inside the bubble. Note that the cut face in the free body diagram is a left-hand face. In other words, the outward normal from the face points to the left. This means that the positive directions for the internal forces is reversed compared to the previous 2 cuts, where we were dealing with right-hand faces. Summing vertical forces shows that the shear at X is minus 30 kilonewtons. Draw this result on the shear force diagram. And, taking moments about the cut, shows the unknown bending moment is plus 30x kilonewton meters. That is, the bending moment varies linearly from 0 at D to plus 60 kilonewton meters at C. Draw this result on the bending moment diagram. Of course, we could have considered the substructure to the left of the cut, just as before. This would yield exactly the same results. Dr. Jim suggests that you give it a try. Inspection of the bending moment diagram shows that the 120 kilonewton meter applied moment causes a 120 kilonewton meter step on the bending moment diagram. This is another universal truth to be added to the list of truths discovered in previous videos. And here is the updated list of truths. 1. Bending moment is 0 at the ends of simply supported beams. 2. Axial force and shear force are constant between loads. 3. Bending moment varies linearly between loads. 4. Shear force varies linearly under a UDL. 5. Bending moment is parabolic under a UDL. 6. A transverse point load causes a step change in shear force. 7. A transverse point load causes a change of the slope of the bending moment. 8. An applied moment causes a step change in bending moment. These laws apply to all beams and frames, both statically determinate and statically indeterminate. In fact, these laws are gold dust, as they make drawing axial force, shear force and bending moment diagrams much simpler. You will have noticed that the screen has been tidied up at various points during the analysis. This was done to free up screen space and is fine for an educational video like this. But when solving problems on paper, all the working should be retained. It might be worth marks after all. And that concludes the analysis. If you would like free, printable, annotated notes for this video, then swing by Dr. Jim's website at drjimstructures.com. Well, thanks for watching. If you found this video useful, please give it a like and feel free to comment. Your feedback is appreciated. Bye for now. Hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.